Hello, everyone. Welcome. I believe that I have things worked out a little bit better today, so hopefully there won't be that weird sort of flipping back and forth. But today is going to be our first kind of acid base AMA. We already had a couple of questions two that were submitted ahead of time. But if you do have questions, go ahead and start putting those in the chat because there is a little bit of delay. I want to just go ahead and kind of get a backlog of questions. That way I can begin to just kind of answer them as we finish instead of just like waiting. And we're just going to go ahead and jump right in. The first question that was asked is about how we compare kind of pKs and pHs, and specifically how this is going to pertain to charge. And we'll go ahead and look at the questions or at this concept first, just sort of in general with pKs. And then since the question was also asked in the context of amino acids, we'll look at it in the context of amino acids. And I'm going to give you kind of my technique for solving these problems because I found that they can be a little bit tricky. So we're going to look at this arsenic-containing compound that I have right here. And it's basically just listed a bunch of different pKs. These don't really pertain to a particular OH. It's just like, okay, whichever OH loses is pK1. That's the one that loses first. And then the second one is just whichever one's going to come off. And you can see that there are some different values. And what I will often do when I'm kind of trying to figure out what I'm going to see is I will kind of create this little chart down below, and I'm just going to put all my pKs on it. And the reason that we're going to do this is because when we compare the pH and the pK, we're trying to figure out kind of what is happening with the hydrogenation status of that particular spot. So what I'll do is I'll just take this pH 8 and I'm going to kind of put it on here. So I would say, okay, 8 is right about here. And what you can begin to think about is that now that we've sort of put everything on this exact same pH scale, we can just ask ourselves, is this pK relative to the pH that we have, either an acid or a base? So for example, if I look at 2.2, 2.2 is lower, which is usually more acidic than 8. So I know that in this particular instance, that first pK value, well, that's going to, at a pH of 8, act like an acid. What do acids do? Acids lose hydrogens. So if this was this molecule in a pH of 8, one of those OHs, the pK1, would be converted to an O-. And so we can see how this is going to begin to change the charge. And since we've already defined what that 2.2 would do, and we just do the exact same thing for 6.9, anything that's basically on one side of this, so anything that's on this side here, it's going to act like an acid, which means that once we know what one does, we know what the other one is going to do. On the other side of this particular scale, we can begin to go ahead and think about 11.5 and what would be happening here, just to sort of take this 100% full circle. So if we look at 11.5 and we'd say, okay, well, 11.5 is a lot greater than 8. Remember, we're always making this comparison. We're going to look at the difference between these two. So for instance, here, we're like, oh, 11.5 is more basic. It's going to act like a base. Well, what's the base form of an OH? That's just OH. It doesn't change. And so it wouldn't have any difference. So in this case here, if we were trying to figure out at pH 8, what would be the net charge of this? It's just -2. And then as I'm going through this, if there are any questions, go ahead and feel free and ask. Because this concept can be a little bit confusing, I have a couple more that I want to go through. So let's say that we were to change this pH, exact same setup, but we're changing the pH, and now it is a pH of 5. We basically just do the exact same thing. So I'm going to just go ahead and put my 5 here. And now, once we kind of get the hang of this, I'm like, okay, 2.2, that's like the acid. So this is going to act like an acid. It's going to deprotonate. So that's this one OH. It's going to go to O-. And then everything else is on the other side. We know that these will just be the opposite. So both of these are going to act like bases. So we're going to have two that are going to remain as OHs. So at a pH 5, here we can see that we're getting a shift or a change in sort of what's happening. And in this instance here, now we're only going to have a -1 charge. So we can use this rather than trying to memorize, okay, is pH greater than pK or is pK less than pH and what's going to happen? I really like this because it's just sort of following how acids and bases work and just comparing, okay, is that pK of 2.2 more acidic? If it is, it's going to act like an acid. It's going to deprotonate. Oh, is that pK more basic? Oh, it's going to act like a base. What does the base form of something look like? So let's say that we want to then go and put this into the context of amino acids. And we'll look at two different amino acids and we basically do the exact same thing. So in this case here, what we're going to have is leucine on the left and histidine on the right. And with a lot of these, and we're thinking about charges, you really only need to, for the most part, think about the side chain. And if you have those memorized, you're pretty good. But let's say they give you some kind of like different pHs. We want to figure out what's going on. Then we'll go ahead and begin to kind of look at some of those. And I'm noticing I need to zoom out a little bit so people can see this. Okay, so again, it's the exact same sort of process, except for leucine, we doesn't really have a relevant side chain here. So if we put pH 1, right, in both of these cases, we're just going to put 1 here. We'll put 1 here. And we want to think about what is it that we're going to see, what's going to happen with these different pieces. So for example, if we're looking at this guy here and we're saying, okay, both of these are on the basic side. So 2 is more basic than 1. 10 is more basic than 1. Both of these are going to end up acting like bases. But this is where things change a little bit because we need to think about, well, this pK of 2, that's the carboxylic acid. What is the base form of that? The base form of a carboxylic acid, or the protonated form, it's actually neutral. It's uncharged. Well, what is the base form of the amine? That's where things are going to differ. That is actually going to be charged because the base form of this NH2 is NH3+. So at pH 1, the charge of a leucine molecule would be +1, and that's coming from the amine. If we were looking at histidine, right, we can see that all of these are going to end up being bases, or in their base form, because they're more basic than that pH. And again, we just think about what would these look like. So this would still be that carboxylic acid, so that would be 0. This guy would still end up being the NH3+, but in this case, we also have to take into account the histidine side chain. And the histidine side chain in this instance is also going to be positively charged because it's a base, and when they gain their protons, they tend to become positively charged. So in this instance here, this overall charge would be +2. And we can just essentially repeat this exact same process for a variety of these just to get the concept down. And I'm going to kind of go through these really quickly just so that you kind of get the sense. So again, we just plot this out. 5 is going to fall between 2 of these. We know that this 1 over here on the left is more acidic, so it's going to be in its deprotonated form. This guy over here is going to be in its base or protonated form. And this is sort of what we're expecting when it's in that more kind of like normal, quote unquote, normal pHs, or within the range of normal pHs. So this is going to be now your O- because it's deprotonated. And this is still going to be your NH3+ because it is protonated. And that's neutral or zwitterionic at that point in time. We repeat this for the histidine. Again, we just put 5 on here, so we can put 5 right there. And we can see the exact same thing again. So this guy is going to be the acid. So acid. And then we flip over. Both of these are going to be bases. And again, we just repeat this. So this is going to be the carboxylate. This will be a positive charge because histidine is a base, so it's going to be positively charged. And then this guy right here is your NH3+. So in this case here, this is now +1, which is why we say that at neutral pHs, right, if we move this little dot over here to around neutral pH of 7, you can see that histidine is going to be deprotonated. But in this particular instance, it's still protonated because it's at pH 5, which is why in this instance, we would see histidine with +1 charge, and why histidine can be a little bit confusing because it's actually pH dependent. We'll go ahead and look at this last example, and then we'll go ahead and move on to the next one. And then I see there are quite a few questions, so we'll start to move on to some of the ones in the chat here pretty quickly. So this one, right, 2 and 10, we're just going to go ahead and put 11, 11. So looking at all of these, now all of these are more acidic. So all of these are going to act like acids in both instances and be in their deprotonated form because that is what acids do. So this guy would be the carboxylate ion. And instead of this guy being in its NH3, it's going to be NH2, so it's neutral. So this would have an overall -1 charge. And then if we look at this guy over here, again, this would be your carboxylate. The histidine in this case is going to be deprotonated, so it's just a neutral histidine. And then again, this is going to be in the NH2 form right here. So hopefully this kind of makes sense, and you can use this when you're solving these problems. It doesn't just have to be for a amino acid, right? They could give you a equation, like a chemical reaction, and then they could give you the pK values, and you would essentially just repeat this exact same process, and then you would know which direction to go or which species would be favored. Okay, cool. Then we'll go ahead and kind of look at this next concept. And the next concept is going to be discussing the acid-base extraction. So this is sort of acid related in the sense that it's definitely more kind of falling into the lab techniques, but it's still going to be kind of acid-based. So I want to talk about the lab technique piece first when we're talking about these extractions, and this is where an acid-base extraction kind of differs. When we talk about things being polar, we're really talking about charge. So in an acid-base extraction, if you're going to be in that aqueous component, you are going to be charged. If, on the other hand, you are uncharged, you're going to be in the organic component. The reason this matters is because if we take something that's a base and we add an acid to it, that's kind of this first piece that we're seeing here. So we took a base, and this is sort of what we're trying to separate. I'll just go ahead and put this with a little star pointing to it of saying this is what we're trying to separate. What you could do is you could add some acid, and that would, oh, sorry, I got this backwards. That is the second one. All right, let's flip this around. Okay, we are trying to analyze the acid, and we added some base to it. And what this is going to do is it's going to take that acid, it's going to put it into its negative, and now we can put that into the aqueous component. And if we did the same thing, but we did it sort of in reverse, right? So we do this in reverse, but this case, we're now looking and trying to figure out how do we separate maybe a base from something else. What you can do is take that base and add some hydrogen to it. If we add hydrogen to it, then just like before, we're going to go ahead and put it into a charged form. And again, we can go ahead and put this into the polar component. So these acid-base extractions are basically going to hook into the idea that we are able to preferentially put something into a charged versus an uncharged state. And the things that you're often going to be separating, you can kind of put them into some categories. If it's acids, it's going to be carboxylic acids and really phenols. Those are really the only two major ones. And so if you wanted to get that acid to end up being in the aqueous component, what you would do is you would go ahead and add base, and now this is going to become aqueous. These guys in the middle that are neutral, it doesn't really matter what you do. You could add acid or base, and in either instance, they're gonna stay neutral. So for example, if we were trying to separate a carboxylic acid and an alcohol, we would add base to this. The carboxylic acid would end up being charged. It would end up in the polar or aqueous portion, and then the alcohol would stay neutral because alcohols really are not acidic. They're like so minimally acidic that they're functionally not acidic. And then it would be in the organic component, and now you could separate those two out. If on the other hand, right, we're trying to separate something that's in this neutral category, say an amide and an amine, and we're trying to separate it on the base right here, we're going to add acid because that is what makes this guy here protonated, and then that's going to end up causing that charge change, and it will go into the aqueous component, and then again you can separate it. So generally speaking, you are going to be separating either things that are acidic from things that are basic, or you're going to be separating things that are acidic versus neutral or basic versus neutral. I would be really, really surprised if they were doing an acid-base extraction and they were having you separated something that was in the acidic category, right? It wouldn't make a whole lot of sense to use this technique to separate carboxylic acids and phenols because there are probably other ways of separating this that would make more sense. This is probably not a great way to go ahead and look at this here. Yes, I did. I did not mean to write base, but sometimes when I am writing and talking at the same time, I write what I don't mean. Thank you. Yes, add acid to the amine. Those were all the questions that were asked ahead of time. So let's go ahead and begin to kind of just look through some of the questions that I can see over here in the chat, and we'll go from there. So this first one is, when we have 2 moles of hydrofluoric acid and there's 100 milliliters of water, the resulting solution has a pH equal to 4. What is the percent dissociation of HF? So the way that I would begin to think about this particular problem is kind of almost starting backwards with what am I solving for? So they want me to figure out what is the percent dissociation. So the first thing that I'm thinking about is what does that mean, right? So like what does dissociation mean, and how would I know the percent dissociation? When I think about percents, I obviously think of something out of 100, and usually that 100 doesn't always have to be 100. Usually it's like some total amount. So what I'm thinking of is, in this instance here, I'm thinking of the actual H plus concentration over like the possible H plus concentration. The possible H plus concentration in this case is probably the exact same as HF, because if we think about what's happening here, HF could dissociate into two pieces, an F minus as well as an H plus. And so if we had 100% dissociation, then the HF concentration would essentially be equal to the H plus concentration. That's kind of my thought process of what is going on with this particular problem. So I sort of chose to start at the end of the problem, which is what is the percent dissociation, and then work my way backwards from that thought process there. So when I begin to sort of look at this here, I'm now thinking they gave me the pH. That probably gives me the actual H plus concentration. And then they gave me the moles of hydrofluoric acid as well as the quantity of water. And that would essentially give me the HF concentration. So I'll go ahead and start with the HF concentration because that seems pretty simple to get. So we'll go ahead and do 2 moles over 100. I'm going to convert that milli into 10 to the negative 3 because that's what it stands for in scientific notation. And this is going to give us the molarity of HF because molarity is just moles per liter. And so then we could go about solving this particular problem. What I would choose to do here with the math is begin by canceling out the zeros in both the 100 and this negative 3. We would have 1 left over because for every negative exponent 0 that you have, you're essentially allowed to cancel out one like positive 0. So this would then be 2 over 10 to the negative 1. Personally, I don't really love doing any sort of division by exponents. So you can always bring these numbers up top if you flip the sign. It's just like multiplying by the inverse. So this is the same thing as saying 2 times 10 to the 1, or just 2 times 10. So this was a 20 molar HF solution. So that's kind of this bottom number that we're going to be picking up here. So we can go ahead and put 20 molar. And we still need the concentration of H plus. And this isn't too bad because we've been given pH. And the way that you convert, whether it's a pH, a pOH, a pKa, or a pKb, for any of these P scales, I'm always going to refer to these things as P scales because I want people to think about them as all the same. So they're all the same thing. The math is the exact same. You just change what you do it to. If we go from the H plus concentration to pH, right? So we're going in this direction. Then what we would do is the negative log. If we want to reverse this and we want to figure out what is the H plus of something else equal to, then this is going to be 10 to the negative pH. So I was saying like, okay, what does that mean in terms of the more general strategy, right? So it's X is equal to 10 to the negative px. Fill in X with H plus or Ka or Kb or OH minus, but I digress. So in this instance, we have a pH of 4. So the H plus concentration in this instance would be 10 to the negative 4. And then we can just plug that in and go and solve this out in this particular case. I would probably just base this off of my answer choices in terms of what the numbers were, but that's how you would go about sort of setting up and solving this particular problem here. So again, just kind of to walk through the steps, and if people have questions, you can go ahead and put that in the chat, and then I'll go ahead and answer them. But I'll walk through the steps so that way people have, just like sitting here waiting. So step number 1, I work backwards. I figure out what does percent dissociation mean. I think about what is dissociation, and then how are percentages usually represented. So dissociation is just the breaking apart of this into pieces. Percents make me think something out of a total, right? So I have a total concentration of what the potential H plus could be, which in this case is the HF. And then I think about, well, what is the actual? That should give me the percent dissociation overall. Then I go about solving for these two particular pieces. So I solve for the HF, and that's just by using the units here, the moles and the liters to actually get the molarity. And then the H plus component is I use that pH to go ahead and solve it, and then I put it together, and then I would just do the math. I don't see any questions on that one. So we'll go ahead and move on and look at the next piece, which is, can we talk about titrations? Of course, we can talk about titrations. And it looks like Specifically, I'm very confused about polyprotic acids and when they get deprotonated. So what we can do is kind of put together the idea of polyprotic acids and deprotonation and sort of how these two pieces fit together. So when you're looking at titrations have a couple different pieces on them. Basically, they look something like this. You have kind of these flat portions, and this would be an example of a polyprotic, and I'll tell you how you can know that it's polyprotic and how you can also know that it's 2. There's 2 hydrogens here. There's not 3 or 4 or some other number. Just going to move this so that it's in the middle. So let's just think about kind of a reaction, just in general, of something with 2 hydrogens. So let's just take H2SO4. So it has 2 pieces. So H2SO4 is going to lose a hydrogen, and then we're going to get HSO4 minus, and then this can happen again. We lose an H plus, and then this goes to SO4 2 minus, just like this. So in this case here, basically, when we have a polyprotic acid, they get deprotonated in steps. So for example, we're going to go H2SO4 to HSO4. And if we have some H2SO4 remaining, as in it hasn't deprotonated fully, we're never ever going to see any SO4 2 minus, because before we see any SO4 2 minus, we literally have to have gotten rid of all H2SO4. It needs to be 100% converted to HSO4 minus. Now, why? Because basically H2SO4, the hydrogen that we're losing, that first hydrogen, is the easiest to lose. So it doesn't actually require as high of a pH to be lost. It could be lost at a pretty low pH. And so we just aren't going to see a change until we actually get a pH shift. And so that's kind of what we're seeing with this particular titration. Now, I want to go ahead and kind of blend titrations and buffers, because in my mind, they really should be blended. When we're looking at these flat portions, these guys right here are your buffer regions. And this kind of makes sense to me, because buffers are going to look at how they stay the same, right? So like, how do the pHs not change? And this is where the pH doesn't change. When we think about buffers, we also have the Henderson-Hasselback equation, and it's talking about how, like, oh, if the pH is equal to pKa, then we know that the concentration of the conjugate is the same. Now, why did I bring that up? Because what I want you to remember is that the buffering region is tied to a pKa value. And so these points that we're trying to define, right, the equivalence point or the midpoint and which is which, these guys are pKas, because this is the buffering region, and pKas describe the buffering region. So if we wanted to label this here, this is the pK1 that describes the first hydrogen loss. This is pK2 that describes the second hydrogen loss here. And what about this last portion? Why did I not include this guy? That's excess base. We're not going to really change the concentration at this point in time, because as this titration is going on, since we started with an acid, we're going to add a base, add base, add base, add base, deprotonate, 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 and kind of go from there. So we don't actually include it. Well, what about the portions here, right, in between? Like, why are we seeing this really big pH change? So each of these pH changes is where we're actually transitioning the hydrogen that we're losing. And so what I tell people is, if you want to know how many hydrogens are being lost, look at the transitions, look at the vertical portions. You're going to have 1 hydrogen for each vertical component. So for example, if this had 3 vertical components, it would have been a triprotic acid. It would have 3 hydrogens. But since this is a 2 hydrogen, it's just a diprotic acid. Another way of stating that it's diprotic is to say that this is a 2 normal acid. That just means that it has 2 hydrogens. Normality just is a measure of some particular thing that you distinguish. So usually in acids and bases, we're talking about how many hydrogens do you have that you can lose? Well, H2SO4 has 2, so it's 2 normal, because we just define the normal component as hydrogens in this case. Okay. What about the rest of these pieces? Well, how did we get, right, to this pH change? Like, why do we now see this big pH change? You can imagine, right, that buffering region, it breaks at some point in time. And the reason that it breaks is right before this. Essentially what's occurred is that we are at 100% HSO4 minus. So we don't really have any more H plus left. And so what's been happening this entire time with this H plus is we've usually been adding a base, say that it was a strong base, it's OH minus. This has been going to water. That's why we've not seen a pH change. This pH hasn't been changing because for each H plus that's lost, it's just being neutralized by the OH minus and it's turning into water. But at some point in time, that stops happening because we completely get rid of all of the H2SO4 that could lose H pluses. We see this really big shift before we can actually lose this next HSO4 minus, and that's why we shift up in the pH. And so what does this mean? Well, this means that right at this central portion, right here, we have fully neutralized anything. Well, what must that mean? Okay, so in this case, let's say that we had 1 mole of H2SO4. That would produce 1 mole of H plus, which must mean that in order to form water and completely form water, we must have had 1 mole of OH minus. And that's why we call this the equivalence point, because the thing that's equivalent at this point is the moles of acid that we started with and the moles of the base that we're adding. And that's what we can basically write in here. Now, this is not going to be the case when we get to a second equivalence point. When we get to the second equivalence point, we've already deprotonated the first bit, but we've already added some moles of base. And so, right, we've added this 1 mole, but if we're going to deprotonate this next piece here, well, now this is actually the second mole. So this is a little bit different. In this instance here, the moles of acid are actually equal to the 2 times the moles of base, and that's just because we have a 2 normal acid, and we've already used up 1 mole of that base, kind of getting rid of that first piece. There's not much else that, in my opinion, you really need to know about these particular titrations. And then somebody asked, how does the AMC test titrations as an exam? Because there's some questions that are long and you need some time to solve them. So they could ask you just straight up, like, is this diprotic or triprotic or monoprotic acid? They could ask you about the pK, like what is the pK value of XYZ? They could ask you to solve for the moles of acid at the equivalence point. That I've seen. They could ask about the moles of base. They could ask about the molarity of something at the piece and kind of go from there. And so that's what I would be thinking about with these types of calculations. I'm sure there are like questions. There are probably others that they could ask, but that's what I would think they would ask. And none of those should take too long if you kind of know how to set them up. And then the question is, do all the moles of acid get converted to base? So all of the moles of acid are not getting converted to base. All of those moles of acid are getting deprotonated, and then the H plus that they create is getting completely neutralized by base and getting usually converted into water. And that's kind of what's being displayed right here, where this H plus this OH minus is going to H2O. And this graph, yes, is showing an increase in pH. This would be like a pH of 1. This would be a pH of 14. So we had to have been adding moles of base. We started with an acid, but this could have been flipped. So if you just sort of invert this whole thing over the x-axis so that we're starting with something up here and then it's going to come down and look like this, then that would have just been reversed. We would have been starting with the base and then adding acid to it as we go through. What's the x and y axis? So this x-axis is usually just volume of whatever you're adding, and then the y-axis is pH. It depends. They can vary these a little bit, but that's kind of titrations in a nutshell. I know that this slide is a little bit busy, but hopefully that begins to help you kind of figure this out. Where do the moles of base come from? We add them. So this is something that we add. So if you ever did that experiment in like even high school chemistry or gen chem class, and you're sitting there drip, 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 you were adding the moles of base into the solution. Now, typically you need to find it because it'll give you the molarity and the volume. They don't just give you the moles of base, but you can kind of figure it out. Is the first vertical line always the isoelectric point? It depends. It depends on the solution. So for example, here, right, there's no isoelectric point because, well, I shouldn't say that there's no isoelectric point because the first vertical component could be the isoelectric point, depending on whether or not you have like isoelectricity that's possible. So for instance here, right, we're not having like a amino acid where you have a plus and a minus component that are going to be represented. Here you just have something that's just going to deprotonate and just become negative. So it doesn't necessarily really have an isoelectric point in that same way. If this was looking at amino acids, then you would need to kind of think about it. And for amino acids, the first vertical line should always be the isoelectric point. Wouldn't quote me on that because I'd have to think it through a little bit. But yeah. And then it says the base is what is neutralizing the H plus. You're trying to calculate the moles of that base. So you could calculate that moles of that base, but typically you're trying to figure out the moles of the acid based off of being given the moles of base. So like, for example, let's say that we did a titration and we had a 10 molar base solution and we were titrating with acid and it took 20 milliliters to reach the equivalence point. And they said that we have 1 liter of starting acid, right? So we had 1 liter of starting acid. And then what they want to know is what was the molarity of this acid? So this is all pertaining to base. And we want to find the molarity of the acid, and that would be the moles of acid. So the moles of A over the liter value. So we already have the liter value. That's going to be 1 liter here because that is just there. But we need to know what are the moles of acid in this case. So to do this, we would say, oh, well, I know that the moles of base are equal to the moles of acid. So to figure out the moles of base, we would just take this 10 molar. So that's 10 moles of base per liter of base, multiply it by the fact that we had 20 times 10 to the negative 3. That's for the milliliters of base. The liters of base will cancel. We could do this math, and then, again, that would be like 2 times 10 to the negative 1. I know I'm kind of going quickly here. So we have 2 times 10 to the negative 1 moles of base to reach the equivalent. But remember, the moles of base and the moles of acid are equal to each other. So even though this is the moles of base, at the equivalence point, this is also equal to 2 times 10 to the negative 1 moles of acid. And so then we could go ahead and use this back up here, and we'd say, okay, cool. So this is 2 times 10 to the negative 1 over 1 liter. So that's just over liters. And so this is a 2 times 10 to the negative 1 molar acid. So that's how you would essentially do or set up one of those calculations using the equivalence point. So that's just kind of one example. Hopefully that kind of clears that up. I know there was another question up front. I'll continue to look for questions on this concept, but hopefully that gives you a good sense of the polyprotic as well as titrations and how the two kind of blend together. If you feel like I've left something out, go ahead and put it in the comments and I'll hopefully wrap back around to it. But I did see another question. This is, could we go over examples of pH increasing/decreasing based on a certain compound being added? Oh, one last question. So what is the role of the base? So the role of the base is to neutralize the acid. And the whole purpose of these titrations is to figure out the concentration of your starting acid. So you know what your acid is, but you don't necessarily know its concentration or how much of it you have. And so the base is basically there as something that we know the concrete things about that are controlled that we can add to it. And then we'll know by virtue of doing this process that I just did here, what the starting concentration of this unknown acid is. Okay, so back to that other question. pH increasing/decreasing based on a certain compound being added. So yeah, of course. So I would say even though this is, right, like if we add acid, then we're going to have a decrease in pH. If we add base, then we're going to see an increase in pH, right? It can be kind of deceptively simple sometimes because there are instances where it's not 100% clear that we're dealing with an acid or a base. So sometimes it's going to come down to recognizing, is this an acid, is this a base, and then kind of going from there. But in general, what you'd be looking for is if we saw an increase in pH, then what we know is that we added a base to the solution. If we had a decrease in pH, then we know that we had an acid that was added to solution. So let's kind of talk about, not some of the like really straightforward ones. So for example, if you had HCl, right, that's acid, then you're going to see a decrease in pH. But sometimes these can be a little bit more, I guess, disguised than that. And so I want to kind of talk about some of those situations. I would say bases more than acids. Bases can be a little bit harder to spot that it is actually a base, but there are some things that we can look for outside of the standards like NaOH and LiOH and KOH. But let's say that you had this molecule here and you're trying to say, okay, you have CHCOO minus. So what's going to happen if we add this to solution? Say it's a neutral solution, you add it to water. Are we going to see an increase or a decrease in pH? you want to ask yourself, do you have an ionizable hydrogen, a hydrogen that can actually be lost? This is not going to be a hydrogen that's attached to CH. So like for instance, this guy here, this is a carbon hydrogen. That's not going anywhere. We do have a spot. So then if we look at this, right, there are no other ionizable hydrogens. No other ionizable hydrogens means that this is probably a base. But there are a couple other things that kind of give us a dead giveaway here. So in this instance, the minus. So bases tend to have negative charges. And if we think about some of our extremes, right, NaOH, OH minus hydroxide has that negative charge. That's just because these things tend to want to accept a hydrogen. Now, this isn't always the case because you could say, oh, well, what about NH3, Chris? Well, you're right? Like NH3 doesn't have a negative charge, but what it has lone pairs. So the two things that you can look for to sort of spot bases will be lone pairs as well as negative charges. Now, the negative charges might be somewhat disguised, if you will. So for example, we could also think about a base salt or the salt form of this base. So for example, if we look at sodium acetate, acetate would normally be CH3COO minus, which looks just like this one up here. But if we put a sodium in front of it, this is now all of a sudden, what is that? That is still a base. So another thing to look out for is if you have a positive salt and then it kind of looks like a covalent compound. It's not like NaCl, but it kind of looks like a covalent compound that's attached to. Chances are, or there's a really good chance, that in that instance, you are dealing with a base as well. Acids are a little bit easier to spot. You can kind of look for the reverse. You could look for things that are positively charged. So for example, NH4 plus is the acid form of NH3. And sometimes you'll also see an acid salt. And in an acid salt, we do the exact same thing, except you're going to have a negative ion. So for example, here, this would be something like NH4Cl, because that Cl minus is going to kind of disguise and go there. And then that's what you would see for these two here. So that's kind of what you would expect overall is base versus acid, and then looking into it a little bit more where it can be a little bit trickier and kind of go from there. And then there's a question, can you go over indicators in acid-base titrations? And then the relationship between pKa and indicators and how to find out the pKa of an indicator. I'd be surprised if they ask a question about the pK of an indicator because they should not really have acid-base properties. So what is the point of an indicator? When we're doing these titrations, everything is just a bunch of clear liquids. So we don't know when we've hit the titration point unless we're like plotting the pH out. But that's not always possible, especially back in the day. So what they did is they found these molecules that change, like pH. I guess suppose they get to I guess they do get like protonated or deprotonated, but it changes the color, right? It changes the color of what's going to happen with these. And so you are just going to need to know what this is going to look like. And then from there, your indicator just needs to be around the equivalence point. And so then you would be picking out the thing that is closest to the equivalence point. So that's probably what they're talking about with a pKa then, with those types of questions. Like it wouldn't really be a calculation, but you would need to know kind of like where does the equivalence point occur pH-wise, and then you would be pulling something that is like right around that particular value. So for instance, if we were looking at this guy here, right? Let's just say that that's at maybe 5. You would want an indicator that probably has a pK of around 5 or changes around 5 in terms of that kind of color shift. And so the example was the acidity of each broth sample was evaluated by acid-base titration with a standardized solution of 0.1 normal sodium hydroxide using phenolphthalein as an indicator. Which of the following most closely approximates the pKa of phenolphthalein? So, right, without knowing the specific titration that they're doing, I can't answer the question in that case because we're missing some information. The information we would be missing is where is the equivalence pH-wise falling. Either this would be found in an actual titration that is shown to you, like a picture of it, or you would be figuring it out on the basis of what type of titration you were dealing with. When I say what type of titration, basically what you would be thinking about with that would be, okay, we have this titration that we're looking at. And this titration is centered at around 7. So a titration that is centered around 7, in this case here, was probably either strong base plus strong acid, or it was weak base plus weak acid. So equal strengths. If, on the other hand, this was centered, say, a little bit higher, so say we had the equivalence point, and not the best at drawing that, that's centered here. This is centered towards the base side of things, which is a weak acid plus a strong base. And then if this was an equivalence point that was centered lower, something kind of like that, then that would be a strong acid plus a weak base. And then in that instance, you would have to think about, can I estimate it and go from there? But I imagine they would just give you a titration. So then the other question that was asked about this concept is, since it's diprotic, has 2 equivalence points, which one do you look at? I would look at the question, and the question should tell you which to look at. So you wouldn't just pick one. It would be question dependent. And so the question would have to give you information about, do I look at the first or do I look at the second? They would probably indicate that by either talking about the species. So that could be describing H2SO4 or HSO4 minus. Other than that, you wouldn't be able to answer it because it's not like there's a default one that you just pick. Okay, and then there was a different concept that was asked, and this is, please show quick examples using the equation Pi is equal to pKa plus pK2 divided by 2. Okay, so first of all, let's just talk about what that is, right? So what is mathematically pKa1 plus pKa2 divided by 2? So what is this mathematically? So mathematically speaking, this is the average. This is the average between 2 pKs. So if we look at a titration and we think about where is the average between 2 pK values, right? pK here, the equivalence point is the average between these two. Hi. We might have a puppy interruption. And so when we have this, right, this is where it's going to say that this is neutral. If we're looking at, say, an amino acid and we're sort of plotting these different pieces out, then we can just kind of look at this, I think, a little bit more conceptually, and then I'll actually do the equation. So for instance, this is maybe like the carboxylic acid right here. We'll say that this is histidine again. So this is the histidine side chain, and then we'd need one more. There we go. It's really tiny, but same idea. This guy would end up being your NH3 on this side. So where is this going to be, right? So where is this thing going to be neutral? Well, if it's in amino acids, you can always just sort of remember that the 2 endpoints, right? These are the 2 things that are going to cancel each other out. So what this is really going to depend upon is going to be the histidine's side chain overall. And the way that I kind of remember, well, how do I kind of figure out using this equation which one matters, is if you are a basic. So if you are basic, then everything you pull, you want it to be the basic side. So what do I mean by this? So if we're trying to figure out this, we would take the pKa of the 2 basic components for your basic amino acid. If this was an acidic amino acid, then you would take the 2 acidic pieces. So this is maybe pK of 10, roughly, and this is pK of 6. So if we wanted to know what is the PI, this would be 10 plus 6 all over 2. That's 8. That's how you would go about sort of solving that particular problem. And are there any other questions about that? That's just kind of an example. And you could use this for a big variety. If it was just, say, that leucine example, and we're just dealing with this guy here, right? We're just talking kind of about those 2, yeah, okay. we're looking at those sort of two end points again, and it would just be right between. And so these ones don't really change because in this case, we just take the two extremes, which is your carboxylic acid end, and then on the other side, it's your amine. And so that would just be, right, this is like a pK of 2 all the way down here for the carboxylic acid. This is like a pK of 10. 10 plus 2 divided by 2 is equal to 6, roughly speaking, right? These numbers are not like 100% correct, which is why there's going to be some discrepancies if you were to go look up the PI values for these things. But that's a rough kind of idea of how you would solve these particular problems. I think that is all of the questions that have been submitted so far. And unfortunately, I think that is as long as the puppy is going to tolerate for today. And so hopefully this was helpful. If you guys did like this, it'd be great if you can leave just like some feedback. You can do that in a couple of ways. Eventually, I'll just like make a, I guess, like poll or something that people can kind of fill out, or a form. But another thing that you could do if you have something that you want to see that's a little bit different, is I'll go ahead and just put up my email here. If you want to send me an email with something that you'd like to see different for these AMAs, that would be great, because this is the first time kind of doing this. Alternatively, you could just leave a comment on like any of the posts, or even on the live as well. But as I said, hopefully this was helpful. I hope everybody has a good rest of their evening, and I look forward to seeing people hopefully next week. It's going to be practice problems this time, and I'm going to kind of walk through a basic approach and some tools that we can use for those practice problems, and then we'll actually look at some practice problems using those tools so that you get a sense of how we take a resource and actually apply that material, because that's the most important thing that the MCAT really asks us to do, is apply that material. But other than that, I hope everybody has a good end of their night, and then that's gonna be it. And then somebody said, just saw this was live. How can we stay up to date with the upcoming AMAs? A couple things. So one, posts. I have been posting a thing. So I think if you like turn notifications on for the channel, it should show up. And then they're always going to be at the exact same time. So they're always going to be Mondays at 6:30 p.m. EST. So you could just also put that in your calendar, and it should then, you'll just show up and then be able to kind of come. And then they'll also be posted afterwards. So if you did miss and you're interested and you saw, ooh, some people asked some interesting questions, you can always watch them after the fact. But other than that, hopefully, as I was saying, everybody has a good rest of their evening, and I'm going to tend to the puppy behind me. Bye.